For the introduction. So this work is about trying to figure out what people are searching for on search engines with autocomplete. So autocomplete is a feature found on all the major search engines that provides a list of suggested queries to the user as they type. And this feature is intended to try to make the search results more relevant and provide those to the user quicker. And so what autocomplete is doing is trying to predict what you're searching for before you finish typing your query. Now the key thing that this work that I'll talk about looks at is that as you're typing your query into the search field on the web page, this induces a bunch of network traffic between the client and the server. And despite this traffic being encrypted, we'll see how some of the properties of this traffic leak information about what that search query was. So looking back over 20 years of network-based side channels, all of these works leverage really two basic principles. The first, encryption preserves length, at least in the case of web traffic it does, so packet size can leak information about its contents. And the second, which isn't as widely talked about, is that when you have a client talking to a server and it has to talk to the server with low latency, the events that occur on the client are also preserved in the timing of the traffic between the client and the server. So the time intervals between the events that occur on the client, such as keystrokes, are preserved in the packet inter-arrival times. And so all these works have leveraged these two basic principles in some form or another, and the work I'll describe today is no exception. So looking at information leakage through both packet size and timing. So just a quick overview of the attack. The goal is to try to predict what query a user is searching for, and this is looking only at traffic coming out of the client, so only outbound traffic from the victim's machine. And one of the key ideas here that I'll come back to later in the talk is that the attack combines multiple weak sources of information leakage. So it's combining a couple different sources of information leakage that in their own right really aren't a serious threat, but when you put them together, especially because they're independent, they become a more serious concern. And this idea is really embedded in machine learning, analogous to the idea where we can create a more accurate classifier through an ensemble of weak ones. So in the threat model, we assume the attacker can capture traffic coming directly out of the victim's machine. I'm assuming the victim is typing lowercase English letters plus the space key without any typos or the backspace, and that the autocomplete requests, so the request to actually retrieve that list of search suggestions, are triggered on key down events in the web page. So the attack proceeds in 5 different steps, and each step feeds into the next, so kind of a waterfall model, beginning with the complete packet trace, which includes requests to load the page itself and other page assets and dynamic content. We have to figure out which of those requests, so which of that traffic actually correspond to keystrokes. We want to then tokenize the query, so figure out the size of each word in the query. Build up a dictionary of words for each token and eliminate words from that dictionary based on information leaks through header compression. Rank the words based on their timing. And finally, combine these results with the language model to build up this hypothesis, actually a list of hypothesis queries that the user might have searched for. So first, it would help to look at what's actually in these autocomplete requests. So as you're typing your query into the search engine, a GET request is emitted every time you press a key on the keyboard. So as you're building up the query, we have a sequence of GET requests where just a single character is appended to the query itself that's being built up as you're typing it out. And this partially completed query appears as a parameter in the URL. So these packets, pretty much everything else in these packets stays the same. So if we look at the size of the sequence of requests, the size of the packets is linearly increasing since we only have the addition of a single character with each request. And this makes the keystroke detection problem pretty easy, actually. So if we look at an actual page load for a user searching on Google for the term the lazy dog, we see a bunch of requests here where in this scatter plot, each dot is a packet, and we're looking at packet size over time. So we see a bunch of traffic related to the page load itself and maybe some dynamic content, and then a pause. And then once the user starts typing the query, we see a bunch more traffic. And the problem of keystroke detection, in this case, are actually figuring out which of those requests are the autocomplete requests, amounts to just looking for the longest increasing subsequence of packet sizes. And this is a classic problem in computer science that solves pretty efficiently using dynamic programming. So once we have the autocomplete requests, we can then try to tokenize the query, figure out the size of each word in that query. And this is done by looking at the size difference of each request over the previous. So if we look at the size of each packet over the previous, when each character is added to the query, the packet increases by a byte, but when a space is pressed and that's added to the query, this adds an additional 3 bytes because that space ends up being an escaped character in the URL, so that turns into that %20. So we can pretty easily figure out the size of each word in the query, delineate words based on where those spaces occur. So the next piece, which I'll spend most of the time in the talk on, is information leaked through header compression. So first, just a quick background on HPACK, which is the HTTP2 header compression format, which was developed as based on the Speedy protocol and developed to mitigate a host of other compression side channel attacks. The important thing here that I want to focus on is that in HPACK, string literals are encoded, are compressed using a static Huffman encoding, which means that we can look at the HPACK specification, which tells us exactly for each symbol in the string we want to compress, tells us exactly the bit string and size of the bit string to compress that symbol. And so to compress a string literal in HPACK, we just look up all the symbols in our string and concatenate their encoded bit strings together, and that gives us our compressed string because Huffman code is prefix free, so we just concatenate those together. So previous work looked at how much information is leaked based on just knowing the total compressed size of a string compressed in this way, where we have a preset table to compress our string. So just knowing that this string here, for example, is 22 bits, compresses to 22 bits, it was determined that this leaks relatively little information about the string itself. So this doesn't really tell us much about what that string is. That's because that 22 bits is just some linear combination of symbols in the encoding table. So we know that just that the compressed symbols have to add up to 22 bits and not much else. So this doesn't leak much information. However, in autocomplete, we don't just see the total compressed size of the string that's in our query. We see it after the addition of each character. So if we look at the difference between consecutive autocomplete requests after they've been compressed, we can see the size of the compressed symbol after it was appended to the string. So in this case, looking at the difference between our 22-bit string and 17-bit compressed string, we see the new symbol added was 5 bits, which tells us that this has to be one of these 6 letters in the static Huffman table. Now, in practice, there's 2 caveats. One is that we can't measure packet size differences with the granularity of bits. We can only see byte size differences. And the second is that the string literals that are compressed in this way all have some amount of padding which is unknown to the attacker. So there's some padding to align that compressed string to the nearest octet boundary. But the same basic technique still works in practice. And the way we'll use that is knowing the size of the token that we're trying to figure out what it is in the search query. We build up a dictionary of all the possible bite-sized different patterns for each word in our dictionary for that particular length, and also taking into account each amount of padding for each word. So we end up with 8 not necessarily unique bite-sized different patterns, in this case looking at the cumulative growth of the compressed string as you add each character to each word. We end up with 8 not necessarily unique for each word, and this only has to be done once. Now when we see a new bite-sized difference pattern in this sequence of autocomplete requests, we take that and compare it to our dictionary. So we're just looking for an exact match to this dictionary that we've pre-computed. It'll match some words and not others. The words that it doesn't match can be eliminated because we know that they couldn't possibly have been typed by the user and are not contained in the query. So in this way, we learn some information about what word that query might have contained by eliminating some of these possibilities. So the next step in the attack is ranking the words based on their timing. So this relies on an idea which has been well established, which is that the timing of the intervals between key presses leaks some information about what those keys are. And this is because certain keys on the keyboard are generally pressed in quicker succession than others. So keys that are far apart are usually pressed a little quicker than keys that are close together because you can process those keys in parallel. So this is true for a touch typist, not everyone. So you can gain some information about what is contained in the query based on the timing of the packets because these are highly correlated to the timing of the key presses on the victim's machine. So without going into great detail, this step, I'll just say that I look at using an independent data set, train a bidirectional recurrent neural network to try to predict which keys are pressed based on the timing of the key press intervals, which are manifested in the timing of the packet into arrival times. So those word probabilities are then combined with a language model. So in this case, we're leveraging the low entropy of natural language to try to make some predictions about what that query was. So this is really a game of trying to complete the sentence, figure out which word is most likely to come next following a sequence of words that you've already predicted. So this, through a beam search, gives us a list of hypothesis queries that closely resemble English language. There's a parameter in the model that allows you to trade off weight between the language model and the timing model, which you can read more details about in the paper. But the end result here is that we end up with this list of 50 hypothesis queries that hopefully one of them contains the query that the user actually searched for. So to evaluate the overall success of the attack, I automated data collection using actual keystrokes recorded from human subjects. So these were people copying sentences and phrases from the Enron email corpus and billion word corpus. And these were replayed using Selenium and UI input in a low latency framework, and then capture the traffic coming out of the victim's machine to get all that autocomplete traffic along with everything else and figure out if we can predict what query the user is searching for. So it didn't experience any rate limiting or CAPTCHAs when I recorded this data set. It took about a week, presumably because it actually looked like human subjects actually typing out queries into browsers. So the keystroke detection and tokenization can be performed with surprisingly accurate. So with near perfect accuracy, we can pick out those autocomplete requests and figure out the size of each word in the query. And this was looking at both Google and Baidu, and in 2 different browsers across Chrome and Firefox. The query identification results themselves are modest. So if we look at the percentage of the time that the actual query is contained in that list of 50 hypotheses, 15% of the time for Google and 13% for Baidu. So Google actually uses header compression and Baidu does not. So that's where that small bump comes from between the 2 major search engines. And to give you an idea, using a qualitative example, looking at a query where the user is typing for he's recovering from a sprain, in cases where it gets it right, the predicted queries are either exactly the same or very close to what the true query was. And failure cases occur prominently when either a keystroke is missed, so when the false negative occurs in detection, we end up with the wrong token lengths. And when a false positive tokenization error occurs, we also end up with the wrong token length. So the attack outcome tend to be highly polarized. It either got it really right or really wrong. So finally, to summarize, I think this idea of combining multiple independent weak side channels is an interesting one. It definitely makes the problem of trying to mitigate these sources of information leakage much more difficult because you have to reason about now different sources that might be benign or might not seem so severe in themselves. And this problem, the language model turned out to be key, so provide a lot of, it contributed a lot to the attack success, which kind of underscores how pervasive predictability of human behavior is in all things cyber. And finally, I think there's probably some other opportunities to look for where incremental compression occurs. So looking at web applications with autosave feature or mapping services where you drag the map and you see that GPS coordinate in the URL changing incrementally. With header compression, does that leak information? So thanks for listening to my talk, and code is here, and my contact information. I'd be happy to take questions.
All right, thank you. Go ahead.
Hi, Eric Zhang, University of Washington. Great talk and great presentation. I was wondering if you've thought much about other languages, and in particular, are logographic scripts like Chinese, Korean, Japanese just immune to this attack?
Right, so I have thought about other languages. I haven't pursued it in great detail. Potentially, yes, so I'm not too familiar with how, meaning if we're looking at Chinese characters versus pinyin, would that make a difference? If you're searching for Chinese characters, how Unicode plays a role in this. I think that's definitely an area of future research. Yeah, granted, everything here was in English, and search queries in Baidu are probably predominantly not English-based, so it's definitely something to look into.
Thanks.
Thank you.
Hello, Bobo from Facebook. Great talk. I was wondering if you, maybe not in this paper, but just in general, if you've done any work looking at this for users of mobile devices, or was all of this on laptops?
So yeah, this was on a laptop. So I haven't looked at mobile. Presumably, autocomplete works in a similar way on a mobile device. I think one part of the attack that might not transfer over is the timing, or potentially there's maybe more opportunities for information leakage through timing. So based on how users type into a soft keyboard, or whether they're using swipe or not, is probably something to take into consideration. So yeah, also another interesting direction to
Thank you.
Thank you.
So we have time for one more question. Sorry.
Dan Q. Would it be possible to improve the accuracy of this significantly by repeating the candidate phrases to the search engine and looking at the size of the autocomplete response that comes back? And is that a direction you've considered going in?
And so that was exactly what the side channel leaks and web applications paper did, is looked at the size of the server response. It helps a lot if you can reproduce the size of the server response, which is not so easy in practice because that list of suggested queries is going to be based on geographic location, your search history if you're signed into an account, and so forth. But if you can reproduce it, then definitely server response provides a lot of information, leaks a lot of information.
All right, let's thank Vinny again.